Hi everyone. Today let's talk about Chapter 7, Recurrence Relation. Session 7.1, Introduction to Recurrence Relation. So in this chapter, we will only cover 7.1 and 7.2. How do we write recurrence relation? So first, let's consider the sequence. We start with 1, given any term to get the next one multiplied by 2. So we can have a1 equals 1, and then a2, we multiply the first term by 2, so we get 2, and then a3, we multiply the previous term by 2, we get 4, and then a4 is 2 times 4, we get 8, and then etc. We can get a5 is 16 and a6 is 32. Okay, so how do we find a pattern about this sequence? Okay, so because to get the next term, we multiply the previous term by 2, so we can say an equals 2 times a sub n minus 1, and the relation between the terms and the previous terms, this is called the recurrence relation. Okay. We can also find an explicit formula for this sequence by looking at, okay, you can see the first term is 1, second term is 2, 4 is like 2 squared, 8 is like 2 cubed, 16 is like 2 to the 4. And we want to find, okay, what is changing? You can see when this is 4, we have the power is 3. If this is 5, we have the power is 4. So we see the power, the exponent is changing. And the exponent is 1 less than the index. So that's why a sub n is 2 to the n minus 1. This is explicit formula. Okay, so recurrence relations and explicit formula are two important concepts about sequence. Okay, I can give you a recurrence relation and ask you to find an explicit formula, or I can give you an explicit formula and ask you to find a recurrence relation. Okay, formal definition. A recurrence relation is an equation that relates a term a sub n to certain of its predecessors a1, a2, a3, a sub n minus 1. Inherent to this definition is that the initial condition has to be established for the relation to have a complete definition. So we also need like a1, a2, some initial conditions. Okay, let's continue to look at our examples. First, we want to find the sequence whose recurrence relations equals a1 is 2 and a sub n equals a sub n minus 1 plus 3. Okay, so we have a1 equals 2, and then a2 is 2 plus the previous term, so 2 plus 3 equals 5. a3 is 5 plus 3, so that's 8. a4 is 8 plus 3, 11. a5 equals 11 plus 3, which is 14, etc. So this is the first couple terms. And in order to find an explicit formula, we want to find the pattern. Okay, how do we find the pattern? So look at a2. Well, a2 equals 2 plus 3, right? And then how about a3? Well, a3, we add 3 to a2, so that's like 2 plus 3 plus 3. This is the same as 2 plus 2 copy of the 3. And then a4 is we want to add one more 3. So then that's why we get 3 copy of 3. How about a5? We add one more 3. So we have 4 copy of 3. And then we want to ask what is changing? So here, what is changing? you can see the 4, the power, okay, no, sorry, the copy of 3 we add to it is changing, right? This 2 and this 2 and this 3, they stay the same. Okay, so we look at what is changing. All right, so in general, a sub n is, so 2 stay here, and then next, when the index is 4, the number of 3 is 3. Okay, so it's like 1 less than the index. So that's why when the index is n, then we have this guy is n minus 1 times 3. And what is that? Well, that's 3n minus 3. So 3n 2 minus 3 is minus 1. Okay, so we get an explicit formula, and we know our n starts with 1. Okay, and actually this sequence is an example of arithmetic sequence. Arithmetic sequence, the difference between two successive terms stay the same. Alright, let's continue. Example 2. Find the sequence whose recurrence relation is f equals f n minus 1 plus f n minus 2. Okay, so we have the first term is 1, second term is 1, and then the sum of the previous two terms, 1 plus 1 give us 2, and then the sum of the previous two terms, 1 plus 2 is 3, 2 plus 3 5, 3 plus 5 8, 5 plus 8 13, 13 plus 8 21, 21 plus 13 34. And actually this guy is the famous Fibonacci sequence. Okay, and here I give you the picture. So when you make the squares with those width, you can get a nice spiral. And actually you can get this nice spiral in the nature. You will find this spiral in a lot of plants, flowers, and shells. Okay, animal shells. Very beautiful. So please Google Fibonacci sequence for more amazing pictures. Okay, let's continue. Find the sequence whose recurrence relation is in equals 1.1 I sub n minus 1, I0 is 1000, and greater or equal to 0. So you can see this example, our index starts with 0. Okay, we want to get an explicit formula for it. So we start with I0 is 1000. And then we have I1. I1 is 1000 times 1.1. So that is 1100. I2 is 1100 times 1.1. So that is 1210. And then I3, we use 1210 times 1.1, and we get 1331. Please type this in your calculator and see whether you get the same numbers, okay? And then how do we get I4? We can multiply 1331 by 1.1. Then we get 1464.1, etc. In order to get explicit formula, we also need to find the pattern. Okay, so pattern I1 is 1000 times 1.1. I2, what do? We multiply by another copy of 1.1. So it's like we multiply 1.1 square. And then I3, can you guess what happened? We multiply by 1.1, but this now is cube. Okay. What is changing? Is the 1000 changing? Is the 1.1 changing? No, the exponent of it is changing with the index, and it's the same number as the index. That's why in is 1,000 times 1.1 to the n. And here our n starts with 0. Yeah, our index can start with any numbers, okay? Not only the start with 1. And actually, this guy is an example of geometric sequence. Okay, so this is geometric sequence. Have you heard of this before? Arithmetic sequence and geometric sequence. So geometric sequence is the sequence, the ratio of two successive terms stay the same. All right, let's continue. Find the sequence defined by the recurrence relation. A1 equals 2, A2 equals 3, and A sub n equals A sub n minus 1 plus 2 times A sub n minus 2. Okay, so let's see. We have 2, and so this is A1, A2 is 3, A4 is the previous term plus 2 times A1, which is 2. Well, that is 3 plus 4, and that is 7. And then A5, what is A5? A5 is 7 plus 2 copy of 3. So 2 times 3 is 6, 7 plus 6, 13. And then A6, well, A6 is 13 plus 2 copy of 7, 14 plus 13, 27. Oh, you see what happened? I counted wrong. So A1, A2, and then it should be A3, right? And then it should be A4. So sometimes it's very important to check our work. Okay, so sometimes we can find our mistakes and fix it. So then A6 is 27 plus 2 times 13. So that's 26 plus 27. What is that? 53. Okay, so let's stop here. But in the exam, I will tell you how many terms you need to find for your sequence. For example, I can ask you to find the first 4 terms of the sequence. Then you know where to stop. Okay, so far so good, everybody. Let's look at more interesting examples. So this example, we want to find a recurrence relation for n bit strings which do not contain 111. All right, so we let Sn be the number of n bit strings which do not which do not contain 111. Okay, so let's look at from the easiest case to the more and more bits. Okay, the easiest, we have 1 bit. Well, 1 bit is either 0 or 1, so S1 equals 2 because we have 2 strings, right? For 2-bit string, so we can have, it's like we have 2 boxes. Each box will fill with 0 or 1. Each box we have 2 choice. So 2 times 2 is 4. And there are 0, 0, 0, 1, 1, 0, 1, 1. Okay, so S2 is 4. Well, how about 3-bit strings? So 3-bit strings, we have 3 boxes. Each box we can fill with 0 or 1. So that's why we get 2 times 2 times 2, that's 8. And we can list them here. 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. So those are only consist of ones. How about we have 2 ones? steps. 1 0 1 1 1 1. So how many do we have? 1 2 3 4 5 6 7 8. Okay, there are all of them. And then we don't want to count the 1 1 1. So S3 is 8 minus 1 equals 7. So far so good. Okay, we want to look for a pattern. So in general, for an n-bit string, okay, so it means we have n boxes, right? Here we have n boxes. Okay, so let's look at the first boxes. Okay, what could the first boxes be? It could be 0 or it could be 1, right? So here we're gonna separate into cases. So case 1, let's say if the first bit is 0. So our picture looks like this. The first bit is 0 and then we have the rest. Well, here, how many bits left? So here we have n minus 1 bit. And this is the string does not contain 111. So, well, this is exactly, so the number of n minus 1 bit string does not contain the 111. This is s sub n minus 1. So the number of strings in this case 1 equals s sub n minus 1. So far, so good. Alright, next case. So when the first bit is 1, well, when the first bit is 1, well, then you look at the second bit. Well, the second bit, it could be 0 or it could be 1, right? So if this is 0, so let's say second bit is 0. Okay, now what happened? Then here we have an n minus 2 bit string. It doesn't contain 111, right? So the number of case 2 is s sub n minus 2. Okay? Alright. So we also, next case, the first bit is 1 when the second bit is also 1. Okay, in this case, what happened? This is 1, this is 1. Well, what is the third bit? Can it be 1? No, it must be 0 because we already have 2 ones here, right? It must be 0. Okay, then how many left? Then here we have n minus 3 bits strings. Okay, doesn't contain 111. So that's why the number of strings in this case equals s sub n minus 3. Okay? Yes. So far so good, everybody? Okay. And here are all the cases, right? Your first bit is either 0 or 1. If it's 0, we're in case 1. If it's 1, then we look at the second bit. Okay, second bit. So the second bit, it could be 0 or 1. Okay, if it's 0, then we are in case 2. If it's 1, then we're in case 3. Okay, so those are all the possibilities. Therefore, we can say hence Sn is the sum of the numbers of different cases. So that's Sn minus 1 and plus Sn minus 2 plus Sn minus 3. Okay, and together with our initial condition, S1 is 2, S2 is 4, and S3 equals 7. So with this recurrence relation, you can see we can plug in S1, S2, S3, we can find S4. and etc. and continue. Okay, so you can see the recurrence relations not only include the terms and the previous one term. It could contains more terms, the predecessors. Okay, predecessors. Okay. All right. So this is our example. Let's continue. Okay, so this example is actually a game. Wow, excited, right? So what is this game about? This is the Tower of Hanoi. Okay, it's a puzzle consisting of 3 pegs mounted on a board and end discs. Oops. So I want a K. Oops. All right. Okay, and discs of various size with holes in their center. It is assumed that if a disc is on a peg, only a disc of smaller diameters can be placed on top of the first disc. Given all n discs stacked on one peg, the problem is to transfer all the discs to another peg by moving one disc at a time. Find a recurrence relation for the number of moves for n discs in the Tower of Hanoi. Okay, so we want to find the number of moves for n disc. So here I give you the picture. We have all this, we have 3 pegs mounted on a board. So we want to transfer all the discs to, let's say, the leg C, okay? That's our goal. So our goal is move all discs from leg A to leg C. Okay, so here I give you an example. When we have 3 discs, first we move the red disc to leg C, and then we move the right disc to leg B, and we move the red disc back to leg B, and then now I have the space and I can move the green disc to leg C. Okay, and then remember we cannot move the red disc directly to C because we want to place the white disc first. So we want to move away the red disc to leg A, and then we can move the right disc to leg C, and then finally we can move the red disc to leg C. So here it requires 7 moves. Okay? So we want to find the pattern. Of course, we don't want to count for like all the discs, right? We want to find a pattern. So let's create some math symbol. Let Cn be the number of moves for n disc. Okay, let's start with the easiest case. When n equals 1, well then we only have 1 disc, then just move it to leg C, and then we're done. So that's why C1 equals 1. Only 1 move, right? And then if n is greater than 1, if n is greater than 1, what do we do? Okay, first we want to move all the n-1 top disc to leg B. Okay, so we want to move all the n-1 top disc. Let's don't say all. Okay, just the top n-1 disc to leg B. Okay, and then we can move the bottom disc to leg C, right? And then now we can move the n-1 top disc from leg B to leg C, and then we are done, right? Okay, let's count the number of moves in each step. Okay, let me change a different color. How about pink? Okay, so when we want to move n minus 1 top disk to leg B. So here, because it's n minus 1 disk to leg B, so this step is actually Cn minus 1. So far, so good. And then second step, when we move a bottom disk to leg C, this is only one move. Okay, and then when we move the n minus 1 top disk from leg B to leg C, this is also Cn minus 1. So therefore, Cn, we sum the moves from each step, is Cn minus 1 plus 1 plus Cn minus 1. So, we have two copies of Cn minus 1 plus 1. So far, so good, everybody? Oh, I'm sorry, some student would cancel the one here. No, this n minus 1 is in the index. We cannot cancel. It's not like a sum or subtraction. So be careful, it's in the index. So here we get a recurrence relation. We have C1. The first move is the first case. Just move one disk to leg C1. So, and then Cn equals 2C sub n minus 1 plus 1. Okay, so this is the recurrence relation. Okay, let's do one more. Okay, so given this recurrence relation, can we find an explicit formula for it? Okay, so how do we find explicit formula? Okay, so we want to find explicit formula. So C1 is 1. Well, C2, 2 times 1 plus 1 is 3, right? C3, 2 times 3 plus 1 is 7. And C4, 2 times 7 plus 1 is 15. Okay, and then let's do one more. C5 is 2 times 15 plus 1 equals 31. Okay, and actually you can see this guy, 3 is like 4 minus 1. 4 is like 2 squared minus 1. 7 is like 8 minus 1. So that's 2 cubed minus 1. 15 is like 2 to the 4 minus 1, right? And 31 is like 32 minus 1. So 2 to the 5th minus 1. So that's why we get a general formula. Oh, no more space. So Cn is 2 to the, so you can see if this guy is 4, this guy, the power is 4, so that's why it's 2 to the n minus 1. And our n is greater or equal to 1. So this guy is the explicit formula. You might ask, okay, why do we how do we think of like using the 4 minus 1, 8 minus 1, 16 minus 1, 32 minus 1? Okay, so we will revisit this example in our next session. Okay, so in that case, you can understand more. All right. So we will see this example again in our next session. Have a nice day. Bye.